Okay, good evening, ladies and gentlemen. This is your well-rounded math teacher, Mr. Pekar, and we're on to Unit 3, Video 3, solving systems of inequalities, and that's our learning target. I can solve systems of inequalities by graphing. If you want to solve a system of equations, you're basically graphing two lines and you're finding the point where they intersect. Now, if you remember when you're graphing inequalities, you'd maybe graph the line, whether it's dotted or solid. We'll say this one's dotted, and it breaks your graph up into half planes, like half plane A and half plane B. And you got to shade one side or the other. All the points in section A are a solution for this inequality, all the points in section B. And you graph it in something like that. So now when we're solving systems of inequalities by graphing, we're maybe graphing a line and finding that it's shaded on this side, and then graphing a different line and finding it's shaded on this side. We're looking for that double shaded area as our solution. So all our solutions for this one would be in this area. This is only a solution for one inequality, so it's not a solution for the system. This wouldn't be a solution for both inequalities, and this point would be a solution for neither. So here's what we're looking for when we're solving systems of inequalities, a double shaded area, and that's what we're going to work on. Let's see here. Okay, here's our first problem, kind of related to a real world type problem. During one heartbeat, blood pressure reaches the maximum pressure and a minimum pressure, which are measured in millimeters of mercury. It is expressed as a maximum over a minimum, for example, 120 over 80. Normal blood pressure for people under 40 or under the age of 40 ranges from 100 to 140 for the maximum and 60 to 90 for the minimum amount of pressure. So there's a high pressure and a low pressure for each heartbeat. So we're talking about two things here. High pressure or maximum pressure, and we'll call that X in this case. Our minimum call our minimum the low pressure or your Y pressure. Okay? Now there's a couple different ranges here. First of all, for the maximum, it ranges from 100 to 140. So the first thing I'd say is this: X has to be greater than or equal to 100. But also, X has to be less than or equal to 140. That's your maximum pressure. And then Y, your minimum pressure, ranges from 60 to 90. So it's got to be greater than or equal to 60, and it also has to be less than or equal to 90. So there's a little range in there. So let's come over here. Here's the actual graph of what we're looking at, what we just came up with. X is your maximum pressure, and that's between 100 and 140. And if you were going to graph X is greater than or equal to 100, first you'd have to graph the line X equals 100, and that's a vertical line. And you can see that is this line right here. Now when they say greater than or equal to 100, think of numbers that are greater than 100. 110, 120, 130. So it's everything going to the right-hand side here. And then X is less than or equal to 140. Well, it's a vertical line at 140, and you want values less than X. So this box that's shaded in here is basically the range for our maximum. And our minimum, which is Y, when you graph like Y equals 60, to start that graph of Y is greater than or equal to 60, you're looking at a horizontal line at 60 right here. It says, well, Y is greater than or equal to 60, so 70, 80, 90, everything going up was what you would look at for shading. And then finally, Y is less than or equal to 90, that's a horizontal line at 90, going straight across and everything below. This area isn't a double shaded region or it's quadruple shaded region. It's shaded for all of these inequalities here. This is a real world problem. This is kind of what it's going to lead us into in the next section, which is linear programming. This is called a feasible region. So You don't have to memorize that now or anything, or you really don't have to memorize it at all, but that's kind of what we're getting into. We're going to start out small and break up into getting to problems where we're working with real-world problems of feasible regions. Okay, let's set up a little compound inequality here. Not necessarily compound inequality, but solving a system of inequalities. Classy catering needs at least 15 food servers and 5 bussers to cater a large party. In order to make a profit, they can have no more than 34 food servers and 7 bussers working at an event. So we got a minimum and maximum for food servers and bussers. Okay, I'm just going to say this. Food server, we'll use the variable f. Bussers, we'll use b. And it starts out with classy catering needs at least 15 food servers. At least means greater than or equal to. If you need at least 15, could you have 16? Yes. 17? Yes. Could you have 14? No. Has to be more than 15. So F is greater than or equal to 15. Let's do the minimum for that too then. What do we have it here? We have no more than 34, so that means we couldn't have 35, so it has to be less than or equal to. No more than is less than or equal to 34. We need at least, so we need more or less than, or more or greater than 5, so bussers is greater than or equal to 5, but no more than 7 bussers, so that has to be less than or equal to 7. So there's an example of a system of inequalities. And that, if you graph that, it would look kind of similar to this one that we graphed right here. You're going to have a little box, and that feasible region, that area inside there is what we're looking at. So here's a simple system of inequalities. It's just going to be 2 lines, and we have to find that double shaded region. What's nice about this one, they're both in slope-intercept form. That first one right here, I'll rewrite it. Y is greater than or equal to negative 2x plus 4. I'm going to graph that in blue. It's already solved for y. So I can use slope, which is going to be negative 2 over 1, and y-intercept. But the key is this. Is it going to be a solid line or a dotted line? And when you're working with inequalities, if it's greater than or equal to or less than or equal to, it's going to be a solid line. If it's less than or greater than, it's going to be a dashed or dotted line. And that's just a boundary. Okay, that line is just a boundary. Your solutions are going to be all the points to the left or to the right of that line when you break it up into a half plane. So graphing this, I can see that it's greater than or equal to, so it's going to be a solid line. My y-intercept is 1, 2, 3, 4. Slope is negative 2 over positive 1. One has to be negative, one has to be positive. A lot of people would go down 1 and then to the left 1. But it's actually down a negative 2 and over a positive 1. Down a negative 2 over a positive 1. So there's our line. Now this line right here, our first line is just a boundary once again. I need to figure out if I'm going to shade, we'll call this region A and this region B, 2 half planes. All the points in A, like this point right here, could be a solution. If it is, all these points over here would be a solution. But if we had a point over here that's a solution, all these points would be a solution. It's either one or the other. It can't be both. So usually you pick a checkpoint. And the easiest one to plug in is 0, 0. Now 0, 0 is in half plane B. So if I plug it into this equation and it's true, then I would shade the B side. If I plug it in and it's false, 0, 0, we're going to call that the check point. It's false, then I would shade the A side. So plugging in 0 in for y. And x greater than or equal to negative 2 times 0 plus 4. Basically, this is 0 is greater than or equal to 0 times negative 2 is 0 plus 4 is 4. Is 0 greater than 4? No. That's false. So what does that mean? 0, 0 is not a solution for this point. So I would shade, not the B side because it's false, I would shade the other side over here. Okay. All those points on the right hand side of this line are solutions. I'll graph my next line in red. That's also in slope-intercept form. That's kind of nice. It's less than or equal to, so it's going to be a solid line again. Now everyone thinks after you graph it, I have to shade below it. You should always use a checkpoint and see which side of the line you should shade. My y-intercept is -2. You can see my slope right here is 1 over 1. So up 1 over 1. And going back the other way. Down 1, back 1. Negative over negative is a positive. This is a solid line. Now if I was graphing equation, system of equations, I would just go to this point right here. Hey, this is my solution. But it's an inequality now, so I just don't want that point. I want a double shaded area. Okay. I'll use a checkpoint of 0, 0 now. It's above the line now, so we got to be careful. If it's true, I would shade above the red line. But if I plug in 0, 0 into this equation, and it's false, I'd shade below it. So plugging in 0, 0 as that check point. Okay, I get 0 for y. It's easy to plug in, less than or equal to 0 minus 2. Is 0 less than or equal to a -2? A lot of people say, oh yeah, it's less than, but it's a negative number. 0 is greater than -2, so this is a false statement once again. So I'm not going to shade above the line towards 0, 0. I would shade away from 0, 0. So I'm going to shade right here. Now if you look at points, would this point be a solution for the system? No, it's not in the double shaded area. How about this point right here? No, it's true for red, but not for our first line, our blue line. This point, yes. All these points in this double shaded area here would be a solution, and that's what you're looking for. So we're good to go. That's how you'd solve this. So if I asked you, is the point 3, 7 a solution for this system? Well, I'd go over 1, 2, 3, and then up 1, 2, 3, 4, 5, 6, 7 is right about here. Is that in the double shaded area? No. So that's not a solution for our system. Let's try another one here. Okay, this is a good one. Solve the system of inequalities by graphing. We're going to do that again. There's an absolute value inequality in there. Some people think these are extremely hard, but they're not. Second one should be pretty easy to graph. It's in slope-intercept form. Whenever you have an absolute value inequality, like the absolute value of y is less than 3, basically you want values of y, when you plug it into the absolute value, it's less than 3 units away from 0 on the number line. So like I could plug in 2. 2 is less than 3. I could plug in -2 because the absolute value of -2 is +2. That's also less than 3. So basically, it's a compound inequality. The first thing is this. All your values of y have to be less than 3, and all your values of y, flipping this sign, have to be greater than -3. So all our numbers that would make this a true inequality are between 3 and -3. So basically we have to graph these two inequalities right here. Graphing y is less than 3, okay. If you put it in slope-intercept form, it'd be y is less than 0x, because there is no x value, plus 3. What does that mean? That means it's a horizontal line. It doesn't go up at all. It's just a flat horizontal line. So my y-intercept is 3. My slope is 0, so being it's just less than, it's a dotted line right here. Okay? Now, you can plug in 0, 0 as a checkpoint to see where you'd shade, but it's basically common sense. Going up and down now for the y, what's less than 3? 2, 1, 0, everything. I'm just going to draw a little arrow like this saying all these values are less than 3 for y. Graphing this one, it's also a horizontal line again. If you want to put it in slope-intercept form, it's just 0x minus 3 if that helps. Your y-intercept is -3, the slope is 0, so it's just a flat horizontal line. Now think of some values of y that are greater than -3. -2, -1, 0, basically going up. So when I look at this y, the absolute value of y is less than or equal to, less than 3. It's everything between 3 and -3 for your y values. Not necessarily your x, but your y values. So it's kind of like a tube. Okay? I'm not going to shade it. We'll shade it when we're all done. But let's move on to this one right here. Y is greater than or equal to x minus 1. I'll graph it in red. My y-intercept is -1. Slope is, it's 1x, so basically slope is equal to 1 over 1. So up 1 over 1. I usually go as far as I can in both directions. This is a solid line. So basically, I'll put A here for in between the two blue lines and to the left of the red. That could be our triple shaded region in this case, or B. Well, which one do we pick? Well, I'm going to use 0, 0 as a checkpoint again. So plugging it into that second equation, our checkpoint 0, 0. 0 is greater than or equal to 0 minus 1. Is 0 greater than or equal to -1? This is true. So I'd shade towards it. So it's not going to be B, it's going to be this A region. And where I would be shading is in this triple shaded area right here. Okay? So whenever you see these absolute value inequalities, you're basically graphing two inequalities. Okay, and if you have any questions with that, if you struggle with it a little bit, definitely ask for some help from someone else or come up and see me. We'll get you on the right track. Okay, we love slope-intercept form. Yes, we do. Here's our next one. And what I notice about this problem is they have the same slope. When lines have the same slope, they are parallel. So are these two lines the exact same line though? No, they have two different y-intercepts. So what's going to happen is we're going to have two lines like this, and a couple different things could happen. You could shade below that one and above this one. Then this would be your double shaded region. That'd be your solution. You could shade above this one and below this one. What would happen then? No solution. You're not going to have a solution. And then one other thing that happens once in a while, maybe I shade above this line and above this line. Well, where's my double shaded region? It's not shaded here at all. In this area, it's only shaded once. Here would be your double shaded region, and that would be your solution. So one of three different choices when you have parallel lines. So let's get busy here and see what we got going. First of all, slope is 1/4, y-intercept is 4, so I go up to 4 for my y-intercept. Slope is up 1 over 1, 2, 3, 4, or the opposite, and this is a dotted line. Okay, if I plug 0, 0 in for that first equation, we'll call it blue, I'd get, checking to see which side we should shade. 0, 0 is below it, so if I plug in 0, 0 into that inequality and it's true, I would shade down. If not, I would shade above. 0 is less than 1/4 times 0 plus 4, or 0 is less than 4. This is true. So what does that mean? I shade, if 0, 0 makes it a true statement, I would shade towards it. I'm just going to draw a couple little arrows telling me that I shade below this line, so I get a nice clean double shaded area. The second line will graph in red here. My y-intercept is -2. Slope is up 1 over 4, or down 1 back 4. This one is a solid line. They are parallel. Even though I didn't graph that one very well. Well, checkpoint 0, 0. 0, 0 is above this line, so if it's true I shade above, if it's false I'd shade below. 0 is greater than or equal to 1/4 times 0 minus 2. That means 0 is greater than or equal to -2. That's true. So, our double shaded area is everything in between these two parallel lines. All those points are a solution. So would the point 3, -4 be a solution right there? No. It's a solution for the blue line because it's below it, but it's not a solution for the red line. How about 2, 2? Yep, 2, 2 would be a solution for this system. 1, 5? No, it's not in the double shaded area. Okay. This is a good problem. It says to solve a system of inequalities by graphing. Here we could definitely, because it is in standard form, do x and y intercepts. You can do that if you like that. Find your x and y intercepts. You can use the cover-up method. I'm just going to solve them for y because I'm just going to kind of stay consistent. That first one, x minus y, is greater than or equal to -1. Okay, because it's an inequality, you have to be careful because if you multiply or divide both sides by negative, you have to flip your inequality symbol. So solving this for y, I'm going to solve or subtract x from both sides. Negative y, because we're subtracting y, is greater than or equal to -x minus 1. I don't want a negative y, I want a positive y, so I divide everything by -1. That means I have to flip my inequality from greater than to less than or equal to. Y is less than or equal to? Well, negative divided by negative is a positive 1x. And a negative right here divided by a negative is plus 1. So there it is, in slope-intercept form. Y-intercept is 1. Slope is 1, which is equal to 1 over 1. So up 1 over 1. Or I could say negative divided by negative is also positive 1, so down 1, back 1. And this is a solid line. Okay, I'm going to plug in 0, 0 again. If my line went through the origin, like this, I couldn't use 0, 0. Then you're going to have to pick a point like, I don't know, really doesn't matter. How about 2, 1? 2 1's below it. You can plug 2 in for x and 1 in for y. See if it makes it true or false again. So you can't always use 0, 0, but in this case we can, so I'm going to. Okay. Anyway, so I'm going to plug in 0, 0 to see if I shade above or below. So 0 for y is less than or equal to 0 plus 1. Is 0 less than or equal to 1? This is true. So I shade towards 0, 0. So I'm going to just put a little arrow in this direction, meaning I shade below it. For the red over here, move it up here, 3x minus y is less than or equal to 4. I see I'm going to have to divide by -1 again, so I'm going to have to flip that inequality symbol. We'll do that when we get there. Subtract 3x from both sides. Negative y is less than or equal to -3x plus 4. Dividing by the -1. It's not solved for y if it's negative y. It has to be positive 1y. So I get y is less than or equal to, oh wait a minute, I divided by a negative. So I have to flip this bad boy and say this is greater than or equal to 3x minus 4. So -4, that's my y-intercept, up 3 over 1. And this is also a solid line. And plugging in 0, 0 here to check and see which side we would shade. I'm going to get 0 is greater than or equal to 3 times 0 minus 4. Is 0 greater than or equal to -4? That's the question. True or false? It is true. Zeros are always greater than negative numbers. There's 0, 0, so I have to shade towards the 0, 0. Okay, where's my double shaded area? Basically, when you graph two lines and they intersect at one point, you create four regions. Here's A, B, C, and D. I can see that D, right here, is my solution to this system of inequalities because it's the double shaded area. Okay, good. Last one here. This one's a little bit different because we have three inequalities, which is fine. Let's see what we can do here. Oh, shit. Okay, we'll just graph it. That first one we'll graph in blue. That's y is less than. Now it's 3 minus x. In slope-intercept form, you want your x term first. You're going to have to do that by hand. We're not adding it to the other side, we're just changing the order on the right-hand side there. So my y-intercept is 1, 2, 3, and my slope is -1. Well, that's -1 over 1, so down 1 and over a +1. Or I could say that's +1 over -1. So up 1 and back 1. And this is a dotted line. Okay? So where do we shade this one? I'm going to plug in 0, 0 for a checkpoint is 0 less than -0 plus 3, which is basically is 0 less than 3. Yes, it is. This is true. So here's 0, 0. So I'm going to shade towards the 0, 0. Okay, the second one here, we got y is greater than or equal to -1. There is no x value. I can still write it in slope-intercept form. It'd be y is greater than or equal to 0x. 0 times x is just 0, minus 1. What does this mean? The slope is 0. It's a horizontal line with a y-intercept of -1. So I'm going to go to -1 here. This is a solid line. Now I just have to decide if I shade above or below it. You can use the checkpoint 0, 0, but look at this. Think of all your y values. If they're greater than -1, would you be going up or down? You'd be going up. So we have a double shaded region right now. I have to graph that last one. I'll graph that bad boy in red. X is greater than -1. There is no y, so I can't graph this in slope-intercept form. Whenever you have just an x, it's a vertical line instead of a horizontal line. I have an x-intercept at -1 right here. It's going to be a dotted line going straight up and down. Here the slope is undefined. When the slope is up-defined, it's just a vertical line. You could use the checkpoint 0, 0. 0, 0 is to the right of this line now. When I plug in 0, 0, I get 0 is greater than -1. Is that true? This is true. But it's obvious 0 is greater than -1 for x, so you basically are going to be going to the right. And here, not double, but this would be a triple shaded region. Okay? This is what we call a feasible region. You'll be seeing more of this tomorrow, talking about feasible regions, or whenever you get to Unit 3, Section 4. Now, I forgot to read the directions here, but the directions say, find the coordinates of the vertices of the figure. Well, the coordinates of, this is a triangle. Our first vertex is this point right here. Here's another one. And here's our last one right here. The coordinates of that vertex are -1, 1, 2, 3, 4. -1, 4. This vertex is, what do we got? 1, 2, 3, 4, -1. And the last one, this point, it looks like you're over a 1, -1, and down a -1, so -1, -1. It's kind of important to be able to find the vertices because you're going to use those to solve problems when we start working with linear programming in the next section. It's kind of when we apply what we're learning here to the real world. So have at it, and we'll see you tomorrow. Yeah.